Good morning. In this video, we are going to understand how the connection establishment and connection release work in TCP. So first of all, remember that on TCP we have three stages: connection establishment, data transfer, and connection release. So first of all, we have to establish the connection in a way that, for example, one host sends the connection establishment request with a specific flag called SYN. This SYN is for synchronization. So this is an invitation of the connection. Then B can accept or not accept the connection. In case B accepts the connection, it will send a SYN ACK. Again, the SYN flag is active as well as the ACK, saying that I have received your previous segment and I acknowledge the reception of this segment. And finally, A must send a final ACK. So this is the normal process for connecting a couple of hosts in terms of TCP. It is called three-way handshake. I told you that, for example, when receiving the first SYN, B can accept or not. If it doesn't want to accept, it will send a reset flag saying, okay, thank you for your offer, but I cannot accept your request. So this is the normal process for the TCP three-way handshake for connection establishment. The other process after sending data, so after connecting, we are in this position to send data in the second stage, data transfer. And then after that, if we don't want to send anything else, we can disconnect. We can start with the connection release. In this case, the host that will send the first SYN, it's not necessary to be the same that started the connection. So for the connection establishment, the host that sends the first SYN is the client. And the one who received the first SYN is the server. So there are two roles: client, server. Client, the one who sent the SYN; server, who the one who received the SYN. Then for the connection release, for disconnecting, there is no need for being the same client, the one who sent the first SYN. For example, in this case, we assume that also A will send the SYN. B can accept or not. Imagine that it accepts, SYN ACK, and finally the ACK. This is the normal way for disconnecting, but we will see that there are two options: 3 or 4 messages to be exchanged in the connection release. This situation is with 3 messages, but in the future we will see another option with 4 messages. So this is a simple example of TCP connection. On the left, we have the TCP client with the socket with a port above 1023 and in state closed, waiting for connection. He wants to start the connection. Then the TCP server is on the right. IP address and port. In this case, we can see that this is a web server listening for incoming connections. So the client will send a SYN, I want to connect with you. The server will accept, sure, I accept the invitation. And then the final message in the three-way handshake is the, okay, we are already connected. At that point, the client has the connection established. At that point, the server has the connection established. So this is an example of a normal connection establishment with three-way handshakes, three messages: SYN, SYN ACK, and ACK. Okay. After the connection, we can send data. Imagine that the server send 1000 bytes, another segment with 500 bytes, and client says, okay, I have received up to byte 1500. This is a normal ACK. Okay, different number of segments, different sizes. Right, we are in the data transfer. After that, we have to release the connection. But who is the one who wants to start the release, the connection release? For example, in this case, the TCP client is the one who wants to disconnect. He sent the FIN, but in this case, we have the other option for messages. Why? Because after receiving the disconnection invitation, B, TCP server, has to talk with their application. If it is a slow server, maybe the application doesn't want to disconnect at this moment, but he has to send a normal ACK. Wait, I'll notice my application. After that, once the transport layer and the application layer have been talking and say, okay, you can disconnect, the TCP server will send the thing, right, we close, bye. And finally, this is a final ACK saying, see you later. Okay. So in this example, we have a connection release of 4 messages because the TCP server is slow. If we compare this situation with the previous one, here we have 3 messages because in this case the server is quick and doesn't want to wait a little bit for saying, okay, I send you an ACK first and then the FIN. No, in this case, I'm very fast and I agree the disconnection. 3 and 4 messages in this case. So as a summary, for the three-way handshake connection, the segment can arrive to the destination and be duplicated. How? Let's see an example. Imagine that host A send a segment, but this segment is slow in the sense that it's flowing through the network. Imagine that there is kind of congestion in the network. Then, since every segment must be acknowledged, if we don't receive the corresponding ACK after a timeout, I have to retransmit it again. Okay, this is the same segment. But imagine that finally, after a while, this first segment also arrived. It is duplicated. So B needs to use a mechanism to say, okay, this is duplicated, I have to discard it. Okay, but with a simple connection procedure, this kind of duplicates can cause problems and an entire connection could be duplicated. So this is the reason why we send 3 messages in the three-way handshake and not only 2, not only the first SYN and the second SYN. We also add another third segment for the ACK. The first segment sent by the client, the host, which is a client with the role of a client, sends an invitation to connect to the server. So the process is an active open. I'm sending you a connection request. When the server receives this first segment, we'll answer yes or no. I want to disconnect to connect or not. If so, if I accept, I will send an SYN ACK, and the role is passive open. I have received the connection establishment request and I accept. I'm passively opening the connection. And finally, the last third message is a simple ACK. So the client considers that the connection is established after receiving this segment, and the server considers that the connection is established after receiving this segment. How to identify a segment? So remember that there is a field called sequence number of length 32 bits. So at the end, it's a very big number with 32 bits. And when we start a connection, we need to identify a sequence by the initial sequence number, the ISN, initial sequence number, that uniquely identifies each connection try. So imagine that I'm a client, I want to start a connection, I need an initial sequence number. How to get this value? So this value is got by means of the time. So every 4 microseconds, this number is increased by 1. So when the time passes, we will have a different initial sequence number based on time. Since this field is 32-bit length, it has a maximum value, and the initial sequence number will be restarted after 4 hours and 46 minutes. This time is enough for potential duplicates using the same ISN or initial sequence number. So the idea is to avoid problems with previous connections. So normally one TCP connection will not last more than 4 hours. So this is the reason why they have decided to use this process for setting the initial sequence number. Let's see again a three-way handshake. So on the left we have the client, TCP/A client, the socket. On the right we have the server with the socket. Client close, server listening. The client sends the first SYN. In this case, we receive an initial sequence number of 100. Sequence 100, SYN flag active. Once the server receives the SYN, he has to decide, accept or not. In this case, we accept. Another different initial sequence number, because there is a difference in time between this initial sequence number and this initial sequence number. Each host will have a different initial sequence number. Then this initial sequence number is put into the sequence number field, and the ACK is saying, okay, I have received up to 100, the sequence number 100. This flag means that there is a virtual byte in the segment. So the next segment I'm waiting for is 101. Okay. My sequence number is 300, and I include the SYN and the ACK, acknowledging your previous segment. At that point, the connection is established, and then there is one remaining task to be done. The client must send a final ACK. Final ACK, sequence number 101. That means it is the same that B is asking for, and the ACK is the previous segment sequence number I have received plus 1, because this segment has a sequence, a SYN flag. At that point, the TCP server is connected. After that, we can exchange data. Okay? So as a summary, we have the initial sequence number on the left, another one on the right. The fact of having the same flag implies that we have to add 1 byte in the ACK here, ACK 101, because the segment we have received is 100 plus 1, and then the next segment is 101. As a summary, the client selects a unique initial sequence number for each try. It is sent to the server. When the server receives the connection request, it selects another initial sequence number and sends the answer, including it. And then when the client receives the answer, it considers the connection as established. And the remaining task is to send an ACK. Okay, after that, when the server receives the ACK, the connection is already established for it. Now we are going to see specific examples of problems in the network. So the first one is, imagine that there is a delayed scene. So the scene is not correctly delivered in a fast way. So on the left, we have the TCP-A. On the right, the TCP-B. It is a web server listening as usual. And the TCP-A wants to connect with TCP-B. The initial sequence number is 90. A sends a segment with this initial sequence number, but A doesn't receive anything from B, any acknowledgement from B. So A tries again, several times, but A noticed that there is no answer from B. So it decided to close the trials. After a particular period of time, A wants to connect again. Why? Is there a problem with B? I want to connect with that web server. I want to access this website. So he tried again with a different initial sequence number because of time. This time is different from that. So we have a different initial sequence number. In this case, the sequence is 100, flag sync active. It is correctly received by B. Accept the connection. ACK 101 because I have received 100 plus 1 because of the sync. A different initial sequence number on the right side, sequence 400. At that point, the connection is established for A, and the final ACK is sent from A to B. At that point, the connection is established for B, and the sequence number is 101 because it's the one that is requested by B, and the ACK is 401 because I have received 400 plus 1 because of the scene. But one of these things that were sent previously that didn't arrive to the destination, we didn't notice anything about the delivery, finally arrive to the destination. And B can say, okay, I have received sequence number 300, I'm working with 400, what's happening? Okay, don't worry, maybe it's another connection, I accept. But when A receives this segment, it will surprisingly think, I have a connection that is based on sequence number 100, 400. Why am receiving a sequence 300 and ACK 91 since I'm working with 100 and more numbers? So in this case, A says, okay, I have one connection that is already established with B with this sequence number 100. I'm maybe receiving a notification from a previous trial that I discarded, so I want to reset this connection, and we will continue using this connection TCP connection with this initial sequence number. So this is an example of a delayed scene when first there is a trial, no answer from B, then the connection is correctly established, right, perfect, and finally one of these scenes arrive. So we have to reset that connection and continue working with the one which is already established. Another example, same situation, delayed scene, another trial with a different initial sequence number. Again, a delay, but first this thing arrives. So the segment arrives with sequence number 90. The TCP/B accepts because it doesn't know anything about any connection. This is the first segment it receives, so accepting. And then when A receives this segment, it thinks and say, okay, I'm trying to connect again with initial sequence number 100. Why I'm receiving an ACK of 91? Reset. This is not my game. I'm working with sequence number 100. I discarded the previous connection. It is already closed. If I want to connect with B, I will work with sequence number 100. Finally, the segment arrives and the connection is already established. The difference between this situation with the previous one is that in both cases, we have a first trial with sequence number 90. Okay, sequence number 90. There is a delay on the sequence number 90. Then, in this case, we have a connection with sequence number 100. In the final case, there is also a delay on the sequence number 100. But we have to disconnect here, and finally, the connection is here. So in both cases, we have a connection establishment with the initial sequence number 100. But be careful with the delays. There is another type of connection establishment. It's called simultaneous or symmetric connection. In this case, both hosts want to connect at the same time. So there is a scene segment crossing. It's not very frequent, but instead of two connections, TCP is thinking about it and say, okay, we only have one connection. Both hosts send the second message, the SYN ACK, the second one in the three-way handshake, adopting the passive role, the passive open role. And in this special case, 4 messages are exchanged. So let's see an example. In this case, both A and B want to connect. So initial sequence number here, 100, here, 300, okay? So at this point, A knows that it wants to connect with B, but B was also thinking about to connect with A. So if I want to connect with B and B wants also to connect with me, I send the SYN ACK message with sequence number the same as the previous one and ACK number 301 because I have received 300 plus 1 from the SYN. The same situation here. At that point, B knows that A wants to connect with B and B wants to also connect with A. So, SYN ACK, sequence number 300 and ACK 101 because I have received the segment 100 plus 1 because of the SYN. So at that point, the connection is established for A, and at that point, the connection is established for B. Going back to the sequence number identification. So it's a field of 32 bits in the TCP header and counts all the transmitted bytes in a connection. So there is no an incremental procedure in terms of number of segments. So if I send a segment with sequence number equal to 0 with inside 100 bytes, the next one I will send is sequence number 100, not 1. So because we are counting bytes, so this is the first segment, this is the second one, but the sequence number is 0 and 100, because in the first one with sequence 0 we have a 100 bytes inside. Obviously, since there is a maximum value, we have to also reset and go back to 0 when we adopt the final number. As I previously told you, when the scene flag is active, we have to add 1 in the ACK because it's considered as one virtual byte. The ACK number is related to the sequence number. If I receive a sequence, a segment with a particular sequence number, I will answer with another sequence number from my side, starting from the initial sequence number from my side, but asking for the next segment I'm waiting for. Okay? For example, if this sequence number is 0 and it has 100 bytes, as in the previous case, my ACK will be 100. And the next segment that will be sent from A to B is sequence number 100. So the one B is asking for. The next segment that must be sent by A is 100. So this combination of sequence numbers and ACK numbers are used for ensuring that all data have correctly received by the destination. So all the segments in the TCP connection except the first one have the ACK flag active, right? And the simple presence of the ACK flag doesn't increment the sequence number. The ACK is not the same like the SYN or FIN flag when we had to add one virtual byte. No. In this case, the ACK flag doesn't add any virtual byte. So here we have an example of 4 segments that are exchanged between a couple of hosts. So this is the first one, SYN, second SYN, third ACK, 4 data. The fourth one belongs to the data transfer phase. The first one is the first SYN, the second one is the SYN ACK, so flag SYN ACK, and the third one is ACK. Okay. We have the source and destination port, the initial sequence number. There are other fields, but they are not very important at that point. Source and destination port, initial sequence number for the server, ACK number, and the flags. And finally, in the third one, we have source, destination port, sequence number, ACK number, right? So I encourage you to do a TCP exchange network diagram when we have A, we have B, and you can draw the 3-way handshake with these numbers, okay? You have to think about who is the client, who is the server, which is the initial sequence number in both cases, which is the ACK, which are the flags, and finally you have the fourth message, that is the data transfer. Here you have the solution. On the left we have the client, on the right we have the server. We send the first SYN ACK with the ACK ending in 22. That means that I have received 21 plus 1. At that point, the client is connected. At that point, the server is connected. this ACK is the same. So I have received sequence number ending in 01 plus 1 because of the sync. It ends on 02. And finally, the 4 messages sent from the server to the client, and this is the data transfer stage. So the sync increments sequence number by 1, as I told you. Again here, and the ACK is also increased by 1. Okay, so I suggest you to do the exercise by your own. Now that we know how to establish a connection, we are going to start with the connection release to the disconnection. So after sending data, we have to release the connection in the sense that we have to free all the resources from the TCP connection and be able to provide them for a future connection. So there are 2 types, symmetric and asymmetric connection release. The symmetric connection release is very similar than the 3-way handshake in the case of the connection establishment. The connection is composed of 2 simplex circuits. Each host is able to finish one unique circuit, the one on which it is sending data. And when one of the hosts sends a segment with the fin flag active, it's an invitation to the other host to do the same. Okay, so we use the fin flag. The other case, the asymmetric connection release, is totally different. In this case, one of the hosts wants to disconnect at this moment in an abrupt way. So there is no way for continuing connecting with you. And maybe there are some some data that are lost. So in this case, we use the reset flag. I'm asking you for an example, but the example is that, for example, we receive a SYN and we want to not accept the sync connection, so we use the reset. So in this case, we also use the reset flag to disconnect. For example, I press Ctrl+C when running an application, and the connection is immediately disconnected. So let's start with the symmetric connection release. So it offers a reasonable security, but not absolute, that the application data will not be lost. Each host must send a thing that must be acknowledged by the other end only once, and the connection release can be started either by the client or by the server. So in the case of the connection establishment, the host adopting the client role is the one who sends the SYN, but in this case, the server can also start a disconnection, so there is no problem for that. The host starting the connection release performs an active close. So the first one who sends the FIN is adopting the role of active close, while the other performs a passive close. So as I previously mentioned, we can exchange 3 or 4 messages depending on the speed of the dialogue between the transport and the application layers on the server side. After sending the first thing, the connection is half closed. And we will see the difference between half closed connection and half open connection. So we will see the difference. After sending the segment with thing, the connection is alive during a period of time. This is the double of the maximum segment lifetime that is required for waiting for potential data that is in the network. So this lifetime has a different value in the parameter depending on the operating system, normally between 30 seconds and 2 minutes. So we are waiting for potential data that are in the path, but they are not correctly received for the moment. So the symmetric connection release with 3 messages. We have a connection that is established in both cases, and A is the one who sends the first fin and ACK. Remember that all the segments in a TCP connection have the ACK flag active except the first fin. Then, when B receives this invitation to disconnect, in the case of 3 messages, B agrees and sends a fin ACK back with sequence number 300 and ACK 101 because I have received sequence number 100 plus 1 because of fin. So this process of adding one virtual byte is the same in the case of fin than in the case of SYN. And finally, when A receives the acknowledgement, it will send a final ACK. So this process with 3 messages is the same than in the case of the connection establishment. In this case, it's fin ACK, fin ACK, ACK. In the case of the connection establishment, is SYN, SYN ACK, and ACK. But A has to wait the double of the maximum segment lifetime before closing, waiting for potential data that are in the network. After sending the fin flag, the half-closed connection interval is open. And then, on the other case, in the passive close end, the half-closed connection starts after receiving the invitation to disconnect and ends when acknowledging the disconnection. Let's see the difference between 3 and 4 messages. In this case, the server is slow. So B receives the invitation to disconnect, but it is not prepared to disconnect for the moment. It is talking with the application, and the application is a little bit slow. So in order to not force a retransmission of the same segment here, B must send a simple ACK. Okay, I have received your segment, but I'm waiting for my application. Then when B has the acknowledge from the application, he is in this position to send the fin ACK as in the previous case of the 3 messages, and finally A will send the ACK. Again, A is waiting for the double of the maximum segment lifetime before closing, and the half-closed connection are the same. So this is the difference between the symmetric connection release with 3 and 4 messages. As in the case of the connection establishment, there can be a simultaneous symmetric connection release in which both hosts decide at the same time to finish with a connection. So there is a fin segment crossing, like in the case of the connection establishment, but there is a new state closing. Only in this situation, 4 messages are exchanged, and both hosts must wait the double of the maximum segment lifetime before closing the connection. Let's see an example. The connection is established. At the same time, both A and B want to disconnect, fin ACK, fin ACK. At this point, A knows that B wants to disconnect with A, and A wants also to disconnect with B. So let's continue disconnecting. I will agree by only sending an ACK. And this is the only way for TCP to be in closing state, when there is a simultaneous symmetric connection release. At this point, B knows that A wants to disconnect with B, and B wants also to disconnect with A. Okay, let's go ahead. The same. In this case, both hosts must wait the double time of the maximum segment lifetime before closing. So let's talk about the possibility of losing segments using the connection release. So the segment requesting the connection release, the one with fin, can be lost. So after the timeout, imagine that this is lost, this is a fin. After the timeout, this segment is retransmitted. But what about if the ACK is also lost? So after the timeout, the thing is again sent. And it can also be lost again. And this is an infinite problem, let's say, a problem with without infallible solution. So this is the reason why TCP works on a non-reliable channel that is used to guarantee that information is sent. So TCP works on top of IP. And IP doesn't give the security that all data arrive to the destination. So this is the so-called two-army problem. Imagine that there is a war and a couple of armies. The blue army is divided on top of two hills. Only a couple of soldiers on each part of the mountain. And then on the valley there is a white army that is bigger in number. But if both parts of the blue army agree on the time to attack the white army, they are more in number, right? So the idea is to agree on the time. Imagine that this guy is the general and wants to let the other part that tomorrow at 7 a.m. we are going to attack at the same time to the white army. So this guy is sent through the valley, being careful to not be captured by the white army, in order to tell the captain here, saying that my general told me that we have to agree on the time, and tomorrow at 7 a.m. we are going to attack the white army. What do you think? Do you think that this guy will send the blue army part 2 to attack to the white army? Yes or no, and why? Do you think that this captain or or general will attack to the white army at 7? So there is no guarantee on knowing that the message has correctly arrived to the destination. So imagine that this part attack, but this part doesn't attack. They will be died. The same on the contrary. Imagine that they assume that the packet has arrived. The soldier has arrived. But this captain says, okay, I'm not sure if the other end, this one, knows that I have received the message. So if I attack by myself, maybe we are dead. So it's a problem that can be extrapolated to computers network. So in this case, this layer is TCP and this layer is UDP. Sorry, is IP. IP, TCP. IP is non-reliable. TCP is reliable. So if I send a message on top of IP, maybe it is not correctly received. So we have to finally assume some considerations when disconnecting a TCP connection. So let's see. The first situation is the loss of the final ACK. So we send the fin, we receive the fin, the final ACK is not correctly sent. So after a period of time, a timeout, the host 2 ends with the connection. Another possibility is that everything is lost. Loss of second fin. Host 1 sends the first fin, the second fin is not received, so there is a timeout, and host 1 starts again. Fin ACK, and ACK. No problem. The basic behavior of a timeout. The third one, everything is lost but the first fin. Host 1 sends the fin, the second is lost, the third is lost, timer expires, fin again, end timeout, release connection. And then host 2 receives the first fin and anything else. So after a timeout, the connection is also released. And the final situation, the fourth one, is everything is lost from host 1. So we are connected. Host 1 is trying to disconnect. No way. Several trials, several timeouts, release the connection. And host 2 is still connected. This is the situation of a half-open connection. That is different from a half-closed connection, in which the half-closed connection started after sending a thing from a specific host till the acceptance from the other host on releasing the connection. In this case, host 2 is still connected and the connection is half open. Finally, the other type of connection release is asymmetric. So one host wants to disconnect, sending the reset flag. The host sending the reset flag passes to be closed. And the problem is that maybe data on the fly can be lost. So there is no waiting the double time of the maximum segment length time. And the host receiving the reset also passes to close. So let's see an example. The connection is established. A sends data, B acknowledges and sends data, and A wants to disconnect at that point, for example, by pressing Control C on a program. This is a reset. At that point, A is closed. At that point, B is closed, but maybe B has sent data before closing. This data is not received and therefore lost. And this is the TCP state diagram, so don't worry about the possibility of memorizing it. It is not necessary to memorize it. Just to give you an example of the different states in which TCP can be at a particular time. For example, if we are a server, we are listening. If we send a segment with the SYN flag active, we pass to SYN send. If we receive a SYN, we have passed to SYN receive. Once the connection is established, we are here. After sending the fin, we pass to fin wait 1 or fin wait 2, depending on the situation. Closing with the symmetric connection release, closed, and so on and so forth. So this is the TCP state diagram. So it's not necessary to memorize it, but you know, in most of the cases, which type of state you are using depending on the situation. Connection establishment, connection release, 3, 4 messages, slow server, and so on.